Welcome to this course on computer engineering. In this first module, we will explore the foundations of the discipline, combining principles of computer science and electrical engineering. Our aim is to understand how physical hardware and firmware are created, how they interact, and how they power modern technologies. Computer engineering is about more than building computers. It is the backbone of countless devices and systems: smartphones, medical equipment, communication networks, cars, aircraft, smart homes, and even the infrastructure behind the internet. Without computer engineers, the digital world we live in today would not exist. 1.1 What is computer engineering? At its core, computer engineering integrates two domains. Computer science, which deals with algorithms, programming, and software. Electrical engineering, which deals with circuits, devices, and hardware. The computer engineer stands at the intersection of these fields, developing the processors, microchips, memory units, sensors, and controllers that make devices intelligent. They also design firmware, the bridge between hardware and higher-level software. 1.2 Historical context. The field of computer engineering emerged as a distinct discipline in the mid-20th century. Early computers were massive, filling entire rooms, and relied on vacuum tubes and punch cards. As transistors, integrated circuits, and microprocessors were developed, computers shrank in size while growing in power. From these beginnings, computer engineering evolved into a dynamic field that now underpins artificial intelligence, robotics, and the Internet of Things. 1.3 The role of hardware. Hardware refers to the physical components of a computer system. This includes processors, memory chips, circuit boards, input-output devices, and communication modules. A computer engineer learns how to design, prototype, and test these elements. For example, designing a microchip for a smartphone that balances speed and energy efficiency. Creating processors for supercomputers that handle massive amounts of data. Developing circuits for medical devices where precision and reliability are critical. Hardware is the tangible side of computing, the building blocks that make computation possible. 1.4 The role of firmware. Firmware is a special category of software that sits between hardware and higher-level software like operating systems. It gives instructions to the hardware, allowing it to perform tasks correctly. For example, the firmware inside a printer tells it how to receive data from a computer, interpret it, and print the correct symbols on paper. Without firmware, the hardware would remain an inert collection of circuits. Computer engineers often design and optimize firmware to ensure devices operate smoothly and securely. 1.5 Key components in computer systems. To understand computer engineering, it helps to look at the main components of a computer system. The central processing unit, CPU, often called the brain of the computer, responsible for executing instructions. Memory units, such as RAM for short-term storage and flash memory for long-term storage. Input and output devices, keyboards, screens, sensors, and actuators that allow interaction with humans or the environment. Communication interfaces, such as Wi-Fi, Bluetooth, and wired connections that allow devices to share data. Each of these components must be designed with care to balance speed, energy consumption, cost, and size. 1.6 Application areas of computer engineering. Computer engineering reaches into every sector of modern life. Some examples include consumer electronics, smartphones, gaming consoles, smart TVs, and wearable devices. Medical devices, pacemakers, diagnostic equipment, and health monitoring systems. Automotive industry, self-driving cars, advanced driver assistance systems, and in-vehicle entertainment. Aerospace, flight control systems, navigation, and avionics. Communication systems, satellites, cellular networks, and the Internet backbone. IoT and smart systems, connected homes, factories, and cities. This diversity demonstrates why computer engineering is a cornerstone of technological progress. 1.7 Skills and knowledge base for computer engineers. A computer engineer must be skilled in several domains, including circuit design and analysis, digital logic and microprocessor architecture, programming languages for firmware development, networking fundamentals, embedded systems design, system testing and troubleshooting. This combination of hardware and software expertise makes computer engineers uniquely versatile. In this module, we have explored the foundation of computer engineering. We defined the discipline as a blend of computer science and electrical engineering, traced its history, examined the role of hardware and firmware, and identified application areas. We also discussed the broad skill set required by computer engineers. With these foundations established, we now move on to Module 2, where we will focus on advanced concepts, system integration, and the future of computer engineering.